In this video and the next, we're going to take another look at implicit differentiation. In Calculus 1 and earlier in this chapter, we used a method of implicit differentiation that was based on the chain rule for functions of a single variable. In this video, we're going to see a method which actually uses the chain rule for multivariable functions. Theorem 3.5.3. Suppose that f of xy is differentiable and the equation f of xy equals 0 defines y implicitly as a differentiable function of x. Then, as long as f sub y of xy is not equal to 0, dy dx is minus f sub x of xy over f sub y of xy, or written in our other notation, del f del x over del f del y, minus in the numerator. Proof. So if we have f as our function, which depends on x and y, if y is defined implicitly as a function of x, we have another function level here, and for completeness we can draw x going down as well. And so if we're going to use a multivariable chain rule, we would have del f, del x, and del f, del y on those branches, del f, del y, and dy dx, and dx dx, which seems kind of silly, and we'll see that it's going to cancel out in just a moment. So we're going to examine the equation f of xy is equal to 0, and we're going to take the derivative with respect to x on both sides. On the right-hand side, obviously, we are going to get 0, and on the left-hand side, well, we need to apply the chain rule. So we have two branches to get down to x, so we're going to have del f del x times del x plus del f del y times dy dx. This should have been d's as well. dx dx. dx dx is just 1, and so if we bring that over to the other side, we are going to have del f del y times dy dx is equal to minus del f del x, and if we isolate dy dx by dividing, we do indeed get minus del f del x over del f del y. So example 3.5.5 asks us to apply this theorem and to compare it to the methods that we had learned earlier. So we're given an equation x squared minus xy plus 3x squared equals 6, and we're told that this defines y implicitly as a function of x. We're asked to find dy dx by using the theorem and by differentiating as you would have done in Calculus 1. And to verify, of course, that we do get the same answer both ways. So if we're going to use Theorem 3.5.3, we need a function. So we're going to let f of xy be the function x squared minus xy plus 3y squared is equal to 6. So that if f of xy is equal to 0, we have the equation that we're given, x squared minus xy plus 3y squared equals 6. F sub x of xy is the partial with respect to x of this. Oh, is that unequal? That should be a minus. Minus there. I don't know what I said, but it should be a minus. So we're going to take the derivative with respect to x. That's going to give us 2x minus y. The rest are constants and will disappear. F sub y of xy is minus y plus 6y. No, minus x plus 6y. I'm taking the derivative here with respect to y. Therefore, dy dx, which is minus f sub x over f sub y is going to be y minus 2x if I multiply through the negative sign over 6y minus x. Using a calculus 1 method, if we want to take the derivative of a single variable function of both sides of the equation, x squared minus xy plus 3y squared is equal to the derivative with respect to x of 6, well, we still get 0 on one side. On the other side, we have to use the chain rule for a single variable, so we're going to have 2x minus, this becomes a product rule. Derivative of the first is y, derivative of the second is minus x times dy dx, plus derivative with respect to y, 6 y times, chain rule, dy dx is equal to 0. So now we have to isolate dy dx. So let's multiply through the negative sign. 2x minus y plus x times dy dx plus 6y times dy dx is equal to, there's a mistake, who sees it? I see it. There's not supposed to be a minus sign in there. I kept the minus, I factored it out, so I should have a plus here, which means that when this minus sign multiplies in, I will get a minus sign there. That is better. Is equal to 0. So when we move everything over to one side, we're going to have y minus 2x is equal to 6y minus x, all of this times dy dx, and therefore dy dx is y minus 2x over 6y minus x, which is exactly the answer that we got using the theorem for multivariable functions.